States of matter often seems like it's the easiest topic to revise for your GCSE Physics Paper 1, but trust me when I say you have to be really precise with your language, otherwise you're going to lose easy marks. So when we're drawing out particle diagrams, make sure the particles are the same size, make sure the liquid particles are touching, and the solid particles are in clear rows or columns. Now we're going to look first at the properties of solids, liquids and gases, then how do we go about explaining them in a 6-mark answer, for example. So comparing like properties, the shape of each material is slightly different. In a solid, we've got a fixed shape, it doesn't change shape. A liquid can flow to the bottom of a container, and a gas can fill an entire container. Next, we're talking about their density. So a solid has a very high density, liquid has a fairly high density, whereas gas have very low density. A reminder that density is equal to the mass divided by the volume. If you want a bit more detail on how to find the density of different materials, check out my video on the required practical you also need to know for paper 1. The next property is its compressibility. So a solid is incompressible, it cannot be compressed. The same applies to a liquid, but a gas can be compressed or squished, in other words. So next what we're going to look at is how to describe how particles can help explain those different properties. And this is quite commonly referred to as kinetic theory, and basically means how do particles help explain these properties with their behaviour. Quite often questions will just say particles though, make sure you put part of the word particles in your answer. The first thing we're going to talk about is the spacing between the particles. This is quite an obvious one, but in a solid there is no spacing or minimal spacing between particles. In a liquid it's the same, they should be touching, and in a gas they are spread out. The movement of the particles, solid particles do move, don't fall into the trap so they don't move, but they vibrate about a fixed position, meaning they go back and forth but never have an overall change of position. Liquid particles move freely, gas particles move freely as well in random motion at a range of speeds. The arrangement of particles comes up quite a lot in papers. In a solid, the particles have a regular pattern. You could say they're in rows and columns. In a liquid, there is no pattern or an irregular pattern, and the same applies to gases. And the last thing we're going to look at is the forces of attraction, or the bonds between particles. Solid particles have very strong forces of attraction between them, and in a liquid the particles have very weak forces of attraction. In a gas they have no force of attraction at all, mainly because they're so spread out there's no possibility for those bonds to exist. So in a 6-mark question, quite often they will ask you to link the properties to the kinetic theory or how the particles behave. So we're going to have a look now at how these different features about the particles in each state of matter help explain their properties. So the first one I'm going to look at is its compressibility. Solids and liquids are incompressible because there's no space between the particles, whereas gases are compressible because there is space between the particles, or they are spread out. Now the shape of a solid is due to the fact that the particles are only vibrating about a fixed position and they have strong forces of attraction. In a liquid they can flow because the particles can move freely because there is very weak forces of attraction, and the same thing applies for gases. They have no forces of attraction, so they can move freely randomly, so therefore they can flow to fill the container. Now we can use the spacing to help explain the density behind a solid. If they're all packed very close together, a high mass in a very small volume, that's due to the fact there's no spacing between them. They're also in a regular pattern to allow them to do that. In a liquid, again, there's no spacing between them, so they have a high density because they have a very low volume for their mass, whereas in a gas, you have the particles are very spread out, so a high volume, which means a lower density. The arrangement of particles could come up in lots of different questions, but just make sure you know to describe the pattern as being regular or irregular, depending if it's a solid or a liquid or gas. Let's talk next about changes of state between these states of matter. So we should all know a solid to a liquid is known as melting, a liquid to a gas is known as evaporating. Going the other way, we've got a gas to a liquid is condensing, and a liquid to a solid is freezing. To be able to go from a solid to a liquid, or to a liquid to a gas, that requires an increase in energy or energy to be supplied. Whereas to go the other way, gas to liquid or liquid to solid, the substance is going to decrease in energy, meaning it's going to release energy to the surroundings. All these are known as physical changes of state, meaning that there are no chemical changes or changes to the chemical structure of the material. Just like ice melting, you can get the ice back. And mass is always conserved, meaning it's the same before as it is after. Next, let's talk about a really commonly misunderstood topic in this paper, which is that of internal energy. So a substance's internal energy is made up of the particles' kinetic and their potential energy. So kinetic energy we should be familiar with means movement. So in this case, it's the movement of the particles. Now, if particles have a greater movement, so they're vibrating more or they're moving around more, that means the temperature of the substance is greater. The less commonly understood one is the potential energy. This relates to the spacing of the particles, how far apart they are. The higher the spacing of the particles, the less their potential energy. So we can start to add some of these extra properties into our solids, liquids and gases. So the lowest potential energy, because they're the furthest apart, is a gas, whereas the highest potential energy, because they're the closest, is a solid. Conversely, the highest kinetic energy is held by particles in a gas because they have the highest speed, the highest movement, whereas the lowest kinetic energy is in a liquid because even though the particles are moving, they're not vibrating very much overall. Now let's look at an example of how these different internal potential energy changes as a substance is heated. So we're going to use the example of ice. Imagine you had a bunch of ice in a cup or a beaker with a thermometer to measure the temperature, and you were able to supply heat from a Bunsen burner or something like that. What we're going to look at is how the temperature changes with the energy supplied and how the kinetic or potential energy changes as well. So initially, as you'd expect, with more energy supplied, the ice will become warmer, then it will melt, then it will become a liquid, then it will evaporate and it will become a gas. Now what we should notice is that while the temperature increases while it's a solid, liquid and gas, between these states when it's melting or when it's boiling, it has got a constant temperature. That constant temperature is known as a melting point for the melting stage and a boiling point for when it is evaporating. So why is it then that the temperature is constant at these stages? I'm just going to redraw this graph slide to color code it just so we can compare the two different situations. Now when the temperature is increasing, when it's a solid or a liquid or a gas, that is relatively straightforward. All the energy is being transferred to the kinetic energy of the particles, meaning they have higher speed, meaning the temperature goes up. For all the parts where it's changing state, where the temperature is constant, that is because the kinetic energy is not changing. As the temperature is constant, all that energy is going into potential energy, which is going to be changing the spacing of the particles as it is changing state. This energy is being used to break the forces of attraction or break the bonds between particles, and there's no more left over to increase the temperature. So the particles do not increase their movement, they just break apart at those instances where it's melting or evaporating. Latent heat is defined as the energy needed to change the state of 1 kilogram of a substance. So this would occur at the purple points in the graph when it's either melting or evaporating. There are two very technical names given to the two stages it could be. So for a solid to a liquid is known as latent heat of fusion, and from liquid to a gas is known as the latent heat of vaporization. Gas particles can be responsible for exerting pressure in a gas, like in a tyre in a car or a bike. They do that because when the gas particles collide with the wall of the container, they exert a force. Now, when that force is in a specific area, we call that pressure. Pressure is known as force per unit area or force divided by area, which is where pressure comes from. In a gas, the temperature is directly proportional to the pressure, meaning that if I increase the temperature, the pressure is going to increase at the same rate. The explanation behind this is at a higher temperature, particles in a gas have a greater kinetic energy, or they have a greater speed. Now, because they have a greater kinetic energy, they are able to have more frequent collisions with the container. We could say more collisions per second. Don't just say more collisions, it's got to say more frequent. And they also have a greater force because they're traveling at a higher speed. So with that said, more frequent collisions and a greater force means that it's going to be a higher pressure, as we just talked about. The other thing that can change the gas pressure is to have a greater number of particles, like pumping air into your tyre will increase the pressure because there are those more frequent collisions because there's more particles. The last part of this video is going to be talking to separate science students or triple students only, so you do not need to know this if you're taking the combined science course. So the last thing about this topic is to look at how pressure and volume of a gas are related. They're related by saying pressure is inversely proportional to the volume of a gas, given by this expression here. If I was to plot a graph, it would be a curve decreasing like this. If I wanted to prove that they're inversely proportional, I need to multiply values of pressure and volume together, and they should be a constant value, meaning that if they're inversely proportional, if the volume was to double, the pressure was to halve. The explanation behind this is that at a smaller volume, there are less space for particles to move. So therefore, you're going to have more frequent collisions between them and the container wall. More frequent collisions means more force, which means more pressure, as we've just discussed. That's the end of the States of Matter video. And that's the end of state of matter. I hope you found that really helpful. Make sure to revise this topic because it can be one of the trickier ones to answer exam questions on.